Okay, so this is the final session. It's kind of a bonus session here for the review, um, because normally we're going to finish up after 6. I ended up having to delay the Moorfield, the Eastern West Virginia Community College, because I got COVID coming back from Alaska. That was a fun thing on the airplane, and so anyway, that's all gone now, which is good. And so we're going to be holding the Marietta Saturday and Sunday of this week coming up, as I just mentioned. And let me make sure I give you the proper dates: 19th and 20th. So that's in Marietta. And then the Eastern West Virginia in Moorfield is the 23rd and 24th. So that's a Wednesday and Thursday. So I'm just mentioning this because we also record this, and some people will jump in and get that information at a later date. We were just doing that before we recorded. All right. So I really just wanted to give us sort of a cleanup phase here. As you guys have gone through the course, is there anything specifically that pops out that you'd like to have explained or fleshed out just a wee little bit? As far as usually it's the math questions from chapter 7 that tend to frustrate people at the end here. Let me go ahead and hit the whiteboard, and I'll share this. The main math areas, you're going to have like an array, sizing. So sizing an array. And the way we do the sizing of the array with the math questions, the things that I've found is once you get started, that's sort of the biggest issue. How do we get started on these math problems? Well, with the sizing of the array, we're trying to get to a kilowatt. That's kind of how arrays are sized. A 3.7 kW system, a 7.2 kW system. So if we start out with our insulation. So the insulation, and you'll normally find, for instance, if you look up on PV watts at the orientation, let's say we come in and there's 4.6 hours of insolation at that particular site. So we're going from, we have this many hours. It's also telling us, well, what size array do we need? Well, we need to know also what is our daily load. So we'll need to know the daily load. How do we get the daily load? Well, in most situations, you're just going to get the electric bill, and you're going to take your local electric bill. Let's say that you look at your electric bill, and on average, you've got 716 kilowatt hours per month. Well, we need to get this number from 716 kilowatt hours per month to kilowatts. Well, how do we do that? We divide by hours. Well, hours of insolation, divide that by hours of insolation, but that's insolation per day. So when I need to know what's my daily load, I'll take that 716, and then I usually divide it by 30.5 days in a month. So that in this case is going to give us 23.475 kilowatt hours per day. All right. Well, we know how many hours of insolation. So I divide the daily load by the hours of insolation. So that's 4.6. And that's going to give us 23.475 divided by 4.6. I got the 4.6 from PV watts. I plugged in what's the angle, what's the azimuth, what's the location, and it gives me an average insulation. And this is going to give me a 5.1 kW. So that would be the size of my array if it were 100% efficient. But I know my system's not going to be 100% efficient. So I divide that by the inefficiency. Well, what are our normal inefficiencies? Normally, you've got voltage drop. So we try and maintain that somewhere below 2%. We've got our inverter inefficiencies. And in most of the world today, that's going to be about another 2% based on microinverters or inverters. You've got soiling, there's a certain amount of loss due to soiling. Let's just say, and that's just dust and stuff on the panel. So let's say that's about 1%. So I'm going through the derate process. If I'm using a string inverter, because it uses the lowest common denominator, it's going to say, okay, if it's plus or minus 3%, like one of my panels generates 3% more, the other generates 3% less, you use the lowest common, so it's going to be a loss of 3% with a string inverter. But with microinverters, power optimizers, they tend to average that out because every panel operates independently of every other panel. So you can tend to ignore that. Let's say there are connections. So let's throw another 1% in for connections. And so now we're up to 6% loss. And let's just say for good measure, I'm going to figure out there, because there are some other things like downtime, aging of the panel, inefficiencies of some other issues. So I'm just going to throw in another 2% just for good measure, miscellaneous. So now I've basically said this is an 8% inefficient system, which means it's 92% efficient. So I take 5.1 divided by 0.92, and I get a 5.547. Okay, so that's the size. That's going to be kW. So basically, that's how you size an array. Pretty easy. You take what is my daily load demand, divide it by the hours of insulation at that site, and then divide it by the system efficiency. If I go to derate and I get a smaller number, I know I did it backwards, because it just logically, if my system's not 100% efficient, I should not need a smaller array to generate the power I require. I should need a bigger array. So oftentimes a mistake pops up where you take that 5.1 and you multiply it times 0.92, and you're going to end up with a 4.7. Well, if you get a number that's smaller than the original, you screwed this up. You should get a number that's bigger. In this case, we're going to say about a 5.6 kW. Then when we want to go and figure out what size, what system, well, we know it's a 5.6. So then you go out and you select your inverter, you select your panels, and you begin sizing, selecting the components for your system. Everybody clear about sizing an array there? That's one of the easier problems. The other issue that we run into is like a voltage drop equation. I don't know, there's a quicker way of erasing these whiteboards, but I think I just have to make a new whiteboard. But there's something satisfying about wiping out all of this stuff. All right. So if I want to figure out voltage drop, what is the voltage drop equation? Well, there are three equations you got to memorize. First equation is watts equals amps times volts. That's the power equation. That's very useful equation. The other one is Ohm's law, which is volts equals amps times resistance. That's known as Ohm's law. All that that's telling you, excuse me, is that there is a relationship between volts, amps, and resistance. If you know two of them, you can figure out the third one. It's pretty much all you're getting out of that. Same thing, there's a relationship between watts, amps, and volts. If you know two of them, you can figure out the third one. Then the third equation is the voltage drop equation. So voltage drop, and all this is a variation of Ohm's law, equals amps. Well, which amps are we talking about? Typically, we're talking about the IMP off of the solar panel rating, the amps at the maximum power point, times resistance, but now we have to adjust it for distance. Why do we have to adjust it for distance? Is because in the NEC, we've been given resistance for different wires in ohms per 1,000 feet. So we multiply this times twice the distance of our run divided by 1,000 feet. So what we're doing is we're taking the resistance characteristics that we're given and adjusting it for the distance. So for example, if I'm using number 10 AWG copper wire, I know it has resistance characteristics of 1.24 ohms per 1,000 feet. Well, that's great. I'm going to plug in 1.24 ohms here. And let's say that my voltage drop, the amps on my run are going to be, let's just say, I'll pick a number, but 9.6 amps. So that was the IMP off of a single panel. When we hook them up in a string, what happens? Voltage increases, amps remain the same. So the amps of one panel is going to be the amps for the whole string. So I don't need to adjust that. I just took that off of the panel spec. So 9.6 amps times 1.24. Well, that's 1.24 ohms per 1,000 feet. What proportion or what part of 1,000 feet am I talking about? Well, if my cable run, let's just say it's 240 feet from one end to the other, I multiply that by 2 because it's a circuit. It's there and back. So that's going to be 480 feet divided by 1,000 feet. Well, you decimalize that and it's going to be 0.48. 480 divided by 1,000 gives us 0.48. So now I can calculate my voltage drop by taking 9.6 amps times 1.24 ohms times 0.48, and I get 5.71. All right, so basically what that's saying is from one end of the circuit to the other, that 240 feet, I'm going to lose 5.71 volts of power. So whatever it starts out at, it's going to end 5.71 volts less. So what can I do to reduce the impact of voltage drop? Well, I can use bigger wire. That's going to change this number. The bigger the wire, the smaller the resistance. So I could go with 8 gauge wire, whatever. Yeah, that's another solution, is crank up the volts. So I'm right now saying I'm going to lose 5.71 volts. Is that acceptable or is it not acceptable? I don't know. If it's a 12-volt system, well, 5.71 volts, that's going to be almost 50%. I'm going to lose almost 50% of my power. Well, that's clearly not acceptable. Well, what if it's a 240-volt system? Well, now I would divide 5.71, the same 5.71 divided by 240, and now I'm losing 2.3%. Is that acceptable? Yeah, probably. You're right in that range, 2 to 5%. But residential systems can be all the way up to 600 volts. So if I do that, then 5.7, it's going to be less than 1%. Well, that's clearly acceptable. So ramping up the voltage gives us a reduction, not in the amount of voltage drop we're experiencing, but the effect of that voltage drop on the system. Higher the voltage, 5.71 becomes almost irrelevant. Or I could shorten the distance. Shortening the distance is also helpful. But usually you want to design the systems as short as they can be. So hopefully you've already done that. Hopefully the distance is as short as it's going to be. So those are some of the ways that you can deal with voltage drop. I guarantee you're going to have a question about voltage drop on the test. You're also going to have a question about sizing arrays. That's for sure. Let's see, if we wanted to figure out battery bank sizing using lead acid batteries, well, what do we start out with here? We start out the same way that we would start out with a PV array size. We need to know, what is the daily load? So what's the daily load? Let's say you figured it out. It's a small little cabin. It's got about 400 kilowatt hours per month. We divide this by 30.5 days per month. And that's going to get us 400 divided by 30.5, 13.1 kilowatt hours per day. All right, so that's our daily load. That's where we start. Well, in this case, we want to get from kilowatt hours to amp hours. So what do? Well, to get there, we divide by the voltage of the system. So let's assume it's a 48 volt system. So I'm going to divide that by 48 volts. And now I'm going to get 0.273 kilowatts, or no, sorry. Does that sound right? Amp hours. Oh, I need to, just to make it make sense, I'm going to convert this from kilowatts to watts by changing the decimal. So I'm going to say 13,100 divided by 48 gives me 273 amp hours. All right. So in this case, it's not point. We converted it to watts rather than kilowatts. Okay, so if my system were 100% efficient, and if I just need, and if I could use 100% of my battery, and if I just needed 1 day of autonomy, I could get by with a 275 amp hour battery, as long as it's 48 volts. All right, but I know I can't use all of the battery. So what do I want to set this for? Well, let's say it's a standalone system. Typically, we're going to go at about a 50% depth of discharge. So 50% or 0.5 is the same as multiplying it by 2. So now we're going to get, what is that, 5.46 amp hours, doing a 50% depth of discharge. So I can only use half the battery. Now, how many days of autonomy do I want? Well, this is all designed for 1 day. Let's say it's a weekend hunting cabin, so I might want 2 days of autonomy. That would be that I'm using this system without any solar coming in to replenish it. So if I'm doing 2 days of autonomy, now it's going to be 10.92 amp hours. Sorry, not 10, but 1,000. That's 500. That's 1,000. I keep getting my decimal points mixed up. So 1,000. And then the only other thing that I have to worry about is, what is the efficiency of the inverter? The reason I'm worrying about the efficiency of the inverter is this is a standalone system. Here's my junction box or combiner box. Here's my DC disconnect, charge controller, battery. I go from the battery to my inverter, and then I go from the inverter to my loads. So let's say this is my service panel. So this is going out to light bulbs or whatever else. All right, so that's a standalone system. Well, what is the only piece of equipment between the battery and the load? It's the inverter. So I derate by the efficiency of the inverter. So let's say that inverter is 96% efficient. So I would take this number divided by 0.96, and I'm going to get 1092 divided by 0.96, and we're going to get 1137. So now I need an 1137 amp hour string. So I go out and look for batteries. Let's say I find myself a 600 amp hour 6-volt battery. It's going to be a pretty big battery, size of a regular car battery, roughly, maybe a little bigger. Okay, so how many of those do I need? Well, I need 2 strings. I divide this by 600 amp hours. So I need 2 of them. That would give me 1200. That will more than cover that. So I'm going to need 2 strings, but how many in a string? Well, it's a 6-volt battery, but it's a 48-volt system. So I'm going to need to hook up 8 of them in a string. So I'm actually going to need 16 of these batteries. So I'm going to hook them up into 2 strings of 8. And when we do the pricing, we find out each of these batteries costs us $400 times 16. So $6,400 plus about a ton of weight. And it's a really inefficient way of dealing with it. Let's say I wanted to do a lithium-ion battery system, sizing it. Lot simpler process. I would just find out what is my daily load. We already decided that's 13 point, I think I erased something there. So 400 divided by 30.5. Yeah, 13.11. So that's a kW. So I go out and I price the system. If I want 1 day of autonomy, I would buy a 13 kW lithium-ion battery. That's it. All the derating, all the depth of discharge, all of that's already factored in. So very easy to size for lithium-ion. I would go out and buy myself a Tesla Powerwall that's rated at 13 kW. 1 if I need 1 day, 2 if I need 2 days of autonomy. That would be kind of it. A little more expensive, I think. Tesla Powerwall is going to be in the neighborhood of, what do those cost? About $10,000 now, something like that. In that neighborhood once they're installed. So pretty pricey. Any questions about battery sizing? Rather than going through all the other ones, I think what I'll do is the other math that you're going to want to practice is string sizing. So string sizing, what's the minimum? What's the maximum in a string? That's one that you're going to need to know. Voltage drop, as I said, array sizing, battery bank sizing. I think those are kind of it for the math questions. One other thing I want to emphasize for the test is the idea of how do we size our inverter. And it's different based on whether it's a standalone system or a grid-tied system. So it's important for you to understand how the energy flows through the system. This is a combiner box. I'm drawing a standalone system at the moment. This is going to be your DC disconnect. From the DC disconnect, we go to the charge controller. From the charge controller, we go to the battery. So the whole purpose of a charge controller is to control how the battery charges from the array. From the battery, it goes to the inverter. And from the inverter, typically in a full standalone, you're going to have your AC disconnect, which is the main breaker, and then you got your load distribution. So this is a way. Now, oftentimes you're going to have a generator that's added in here, and it just simply hooks up into the inverter. At which point that would be known as an inverter charger. What it does is it senses when the battery gets to a certain level, and it sends a signal to the generator to turn on. And then it takes that power and it converts it to DC and it charges the batteries. So the inverter charger is just saying, all right, when the batteries get low, because the battery is what's running your load, when it reaches a certain preset level, we're going to kick on that generator and we're going to recharge those batteries. Kind of all it does. You're not going to be running your loads from the generator in most cases. You're going to just simply recharge your batteries and let the batteries run the loads. All right, so that's a simple system. Well, how does the power flow through this system? When I turn on a load, for every load I turn on out here, it continues to draw more power through the inverter to the load. As I add more and more load, the amount of power that's being drawn increases. All right, so all of the power is being drawn from the battery through the inverter to the load. It doesn't matter if there is a solar array there. The solar array's function is to take power from the sun and recharge the battery. So think of it as a firewall somewhere in the middle of the battery. The array is sized to charge the battery. The battery is sized to service the loads. Each one can function independently of the other. I can have an array with a battery with no loads. All that's going to happen is it's going to work until it's fully charged, and then it's going to sit there. Or I can have a battery with no array. It's going to go run until the battery's dead, and then it's going to stop functioning. So we want them in combination. The array recharges the battery services the loads. So we size the inverter. So the main question, how do we size this inverter? It's based on the maximum power draw. So if I can turn on, let's say 3,000 watts in combination of all of the loads whenever I'm turning things on, then I need to have at minimum a 3 kW inverter to handle the load that's being pulled through it. If I undersize it, it's going to squeal at me and it's going to turn off. It's like breaking a circuit breaker. You've put too much juice through it and you've basically popped a circuit. If I have an array or an inverter that's, you can burn them up that way, that's for sure, especially cheaper ones. For the most part, more expensive ones have circuit breakers or fuses inside. What if I put a 5 kW inverter and I'm at most running 3 kW through that load? No problem. I just bought an inverter bigger than I needed. It works better that way, in fact. You don't want to run at maximum capacity all the time. So this is how you size your array or your inverter in a standalone system. But in a grid-tied system, things work differently. So here's my array. I don't know why I got a hand there. All right. Here's my junction box or combiner box. From here, I'm going to a DC disconnect. There is no battery, so there's no charge controller. Nothing like that's required. So from here, I'm going to my inverter. From the inverter, I'm going to the AC disconnect. From the AC disconnect, I'm going into my service panel. And then this is the main. And the main goes out to my meter. And then from the meter, I'm going up here to the transformer up on the telephone pole. So that's a grid-tied system, a simple string inverter grid-tied system. So how does power flow through this system? Well, if I turn on load over here, it's going to pull power from wherever it's available. If the sun is shining, the first place it's going to pull it from is the array, because it pulls power from the closest source. In this case, that's going to be the array. So the array is going to draw power through, and it's going to go all the way to load from the array, going through the inverter. All right, what happens if I keep adding loads? Well, it's going to keep drawing power. What happens if I've got more power than what I need? Well, in this case, it's going to service the load, but any extra power is going to feed into the grid, because the grid will act as just another load. And as much power as I'm generating is going to get used up. It's just either going to go to my load or it's going to go to the grid, but it's all going to get used up, and it's all going to flow through the inverter. What happens if I'm not generating enough power from my array? Well, all of the power I've got is going to go to the load, but I'm going to need to supplement that with power from the grid. So whatever's being generated from the array is still going through my inverter, but my loads are also going to be supplemented from the grid. It's important to understand the loads have no bearing on the inverter size in a grid-tied system. None at all. If I can service all the loads, great. If I've got extra power, it's going to the grid. If I don't have enough power, it's coming from the grid. The loads are irrelevant as far as the inverter is concerned. The thing that is of a concern is the size of the array, because all the power that's being generated by the array is going through the inverter. Whether it goes to the loads, it goes to the grid, doesn't really matter. It's going through that inverter. So logically, you might say, okay, well, if this is a 5 kW array, I need a 5 kW inverter. And that would work. That would work just fine. But it turns out it's probably not the most efficient use of your resources. We might be able to get by with a 4 kW or maybe even a 3.5 kW. We can oftentimes undersize our array, our inverter, based on the size of the array without having a significant impact on the amount of generated power. And the reason for this is a thing known as clipping. So I'm going to clear that page. So what is clipping? Well, typically, the profile of power generation from your array is going to look like this. When the sun comes up, it's going to start generating power. When you hit solar noon, it's going to be at its peak. And then the sun sets, it's going to be back at zero. So it's going to be a simple bell curve. That's normally the case. Now, it makes it a lot easier to understand if we're talking just about a single panel, but the same impacts the entire array. So let's say that I've got a 290 watt panel. So if I've got a 290 watt panel, that's what the profile is going to look like. On a STC day, standard test condition day, 25 degrees Celsius, 1,000 watts per square meter, 1.5 atmospheres, we're going to generate at solar noon 290 watts. All right, that's my STC day. And all of the power that is being generated is being produced or is being captured by my inverter. So let's say this is my panel, but it's also the capacity of my inverter is 290 watts. All right, so this is the inverter. This is the panel. Everything's fine. Everything makes sense. All right, what happens if I put a bigger solar panel on the same inverter? So let's say this is a microinverter. This is an IQ8 Plus. It will operate at 290 watts. That's all it'll capture. So now I've decided I'm going to put a 400 watt panel here. Well, now the curve is going to look something more like this. All right, say this is 400 watts up here at peak. Well, I've still got a 290 watt inverter hooked up to it. So all of this power here has been clipped. It's been clipped off. I'm not capturing it. So that on the surface of it looks bad, right? I'm basically saying, okay, I generated 400 watts, but I could only capture 290. But look at all the extra power that you're capturing. All of these on the shoulders is new power that you've captured because you had an oversized panel. So even on an STC day, and bear in mind, STC days are fairly rare, maybe 10% or less of your days. Most days, even with a 400 watt panel, your production curve is going to look something like that. Or if it's cloudy, it's going to look jaggedy like this. So all of it's still going to get captured by the array. But even on those days when it's generating more, you're still going to come out ahead because of the shoulders. Will it? No. No, it will not affect the amps. Or the amps will not affect the inverter to a point. You'll see that the tolerances of these inverters are pretty well published. So the IQ8 8 Plus has operating of 290 watts, but it may say can accept a solar panel of 450 watts to 200 watts. So that's going to be its functional operating range. So as long as you don't put a panel on there that's greater than 450 watts, you're not going to damage the inverter. If you put a 500 watt panel on there, you might fry out your microinverter. But this is known as clipping. Clipping is a thing that we do a lot. The main reason for this is because of the price ratios. Solar panels are getting cheaper. Inverters are still relatively expensive compared to it. So economically, it's probably better to oversize your array, undersize your inverter. You're going to get the best bang for your buck under that scenario. Doesn't cause any problem if they're both the same, but this is what the industry is looking at. And we're kind of looking at a 1.3, maybe even a 1.4 inverter load ratio. So under this scenario, if I had a 400 watt panel and a 290 watt inverter, that would be, what is that divided? 100 divided by 290. That's a 1.37. So that's at kind of the extreme end. That would be our clipping ratio there. So I wouldn't want to go bigger than 400. All right. Any questions? I think that's probably enough for today. Any questions about this or the process? This is our last get together before our face-to-face. Last call for alcohol, right? Okay. Well, face-to-face. What will we do in the face-to-face? Well, the first day we're going to do the hands-on stuff. So we'll spend the whole day working with the labs. And then the second day we'll do the review and then you'll take the examination. So at the end of the second day, you should be completely finished. Then I'll submit them to ETA and you'll get your grades back within a week or so. All right. Okay. Well, I'm going to end this session and I'll see you guys hopefully this weekend or next week, Wednesday or Thursday. All right. Take care. Bye-bye.